Welcome to a lesson with Dr. Powell. Thinking about that gradient idea, let's come up with how we can think about the tangent plane, the equation of the tangent plane to a surface. Some surface and a point. What's the equation of the plane that's tangent right at that point? How could we do that? Well, first of all, maybe we have a function here, f of x, which represents the surface. Let's just, again, make it fairly simple and straightforward, x squared y minus, let's just do 2x y squared. That's fine. Okay, so we get something like this for our surface. And let's suppose that we want to find the equation of the tangent plane right at the point 1, 1. Now, let's write this with a z. X squared y minus 2xy squared. Let's bring that z over. So we get 0 is equal to x squared y minus 2xy squared minus z. Now, it looks like that if we introduced another variable here and made this like a new function, like a g of x, y, z, so we have 3 inputs, then it looks like we're working with this is what you would call maybe a level surface of this function right here. Because this function is 3 inputs, then you have an altitude, which is in a coordinate or dimension that we can't visualize in a 4th dimension here. However, if you set this equal to 0, it's as if you've set this variable to be a constant. So this is like a level surface. So just like with the analogy where the inputs in 2 dimensions, we're looking for a level curve, the gradient or the derivative happened to be perpendicular. The same thing holds here. So the gradient derivative will actually can be represented as of g here. Will actually be perpendicular to the surface for the same reason. Okay, because this represents like a level surface, or kind of like you fix this value. So if you go tangentially along here and you take the derivative and dot it, you're going to get a 0. So because you're not going to change the output of this. So it's kind of nice. So we can end up getting a vector which is orthogonal, perpendicular orthogonal to the surface, just by looking at this, okay, by finding our gradient of g here, or del g in this particular case, and then inputting the specific value that we want on the surface. So in other words, we want to input the point 1, 1, x is 1, and y is 1. Well, what would z be? Well, I have an equation for z. I know that z is equal to this right here on the surface. So this is great. So I can actually get the z value is just by plugging in the x and the y. So 1, 1, and so it's basically 1 minus 2, which is minus 1. So really we're looking at finding what the derivative of g is, but as a vector if you want here. And let's do that. And we're going to plug in these points. Okay, after we do that. Okay, so to do that, we have 3 different inputs in x, y, and z. So we're going to have 3 different so for every input, you get a new column. We only have 1 output, so you have 1 row. Hence, we can think of it as a vector. Okay, so we're going to have something for x, for y, and for z. So when you take a derivative with respect to x of all this, we can get a 2xy, and then derivative with respect to x, you're going to get minus 2y squared. Okay. And that's just 0. Okay, now derivative with respect to y. So that would be x squared minus 4xy. So x squared minus 4xy. Okay, and I'll put commas in here. It'll help me there. So that's derivative with respect to y. So let's just make sure that's accurate. Yeah, I think so. And then with respect to z, it's pretty simple. Those are just constants. With respect to z, it's just negative. It's just a -1. Okay. So that's what we end up getting. And then we can put in these points when z is this, x is that, and y is that. Well, there's only a place to plug in for x and y here, so that's nice. So we plug in x is 1 and y is 1 into this, and we end up getting 0 in that coordinate. In this coordinate, we end up getting a, say, a 1 minus 4, so -3. And for z, we just have -1. Okay. Something like that. Okay, so it looks like delta g at the particular point that we're concerned with, which is 1, 1, -1, for that being the z coordinate, looks like that's just simply going to be 0, -3, -1. So to find the actual tangent plane itself, all we have to do is to take this as our orthogonal vector, and we need just a beginning point. And look, we have a beginning point right there. That's our beginning point. And we can find the equation of the tangent plane based off that point and that orthogonal vector, as we've done before previously. So what we do is we have our orthogonal vector, which is 0, -3, -1, and we dot it with the difference between an arbitrary point in space, x, y, z, the difference of that point and that. We want to ensure that the line from here to here is in the plane. So if we subtract those two, we want that to be in the plane. That'll guarantee that point's on the plane. Okay, and to guarantee it's in the plane, when we dot it with this, we better get 0. So we take the subtraction, x minus 1, y minus 1, and z minus a -1. And that's going to be equal to 0. So then if we work that out, we should get the equation of the plane. 0 times that is 0, -3, y minus 1. And then we get minus 1 times that, minus quantity z plus 1, equaling 0. Okay, right there. We'll just stop with that. That is the equation of the plane that's tangent to the surface right at the point, right when x and y is 1 and 1. Thanks for watching.